Click the bell icon to get latest videos from Ekeeda.
Hello friends, I welcome you all to this video. We are with the 10th chapter of microwave engineering, where we have been addressing so far the transmission of microwave signal onto the strip line and microstrip line transmission lines. Very first of all, in the first topic we have already introduced to both of these transmission line how the essential modification from strip lines to the microstrip line has been done there. So a brief comparison was also made. The advantages with respect to the microstrip lines have also been discussed, and the selected problems were also practiced for strip lines and microstrip line. In the recent previous video, we have added some more information to how exactly the formulation for the characteristic impedance for the microstrip line is done. So it was by the method of comparison with another transmission line, that it is wire over ground. So now let us have the discussion with respect to what are the accounts for the losses while we have the transmission of microwave signal onto the microstrip line. So here we start with our topic, losses in microstrip line. So I hope that we are now very well familiar with what exactly the microstrip lines are. Microstrip lines are the transmission lines for the microwave signal here. Now these are widely used into both of the microwave technology as well as we have the computer technology. Now what are the advantages because of which this has been so popular to be used in microwave technology and computer technology is that it has the economic and technical merit. It provides a very good connectivity with less efforts with another devices, so that the microwave signal can be carried and further processed for different aspects there. Now the fabrication is also easy here. So I mentioned the advantage here, easy fabrication of the microstrip lines here. And the technology that carries out the easy type of fabrication is printed circuit manufacturing. Now let us have a schematic that describes the microstrip line, and then we can further discuss about the actual losses that will be with respect to the microwave transmission with the help of microstrip lines. The three-dimensional cross-sectional view we have represented in this particular diagram. So to see the dimensional convenience, we take the help of three axes that are mutually perpendicular to each other. So let us say they are intersecting into the one point that it is called as origin, represented by O. Assume this is the x direction, this is the y direction, both belong to the plane of the paper, whereas z direction is denoted in a tilted line, but basically it is perpendicular to the plane of the paper, so it is going inwards to the plane of the paper, perpendicular to it, whereas the negative direction can be coming out of the paper at the position of origin here. So now we consider a microstrip line that is running, or it has a length aligned to that of the z axis here, and in this particular structure we have the most important part, that is nothing but the strip conductor. So we have a strip conductor whose width is denoted by capital W, whereas the thickness is denoted by small t here. Now below this strip conductor we have the material that it is called as dielectric material, and for the dielectric material the relative value for the dielectric constant is represented by epsilon r here. So now dielectric material separates out the strip conductor from that of the ground plane here. So I mention here this is the ground plane, and the separation of the strip conductor from the ground plane is because of this dielectric material, which has a height represented by small h here. Now coming to the point that we need to account for the losses while we have a signal that is of microwave type propagated over such a transmission line. So that time the strip conductor and the ground plane, which are made up of the conductive materials, metals in general we can say, and the dielectric material, most possibly the semiconductor material. So both are contributing into the losses here. So therefore the losses, if we are talking with respect to the propagation, in general we represent propagation by the terms of propagation constant gamma that can have the two components alpha plus j times beta, alpha accounting the attenuation, a kind of loss that we shall be dealing with, and beta carries out the harmonic variations with which we can have the phase changes to occur, so that the propagation into the forward direction of z can be considered. So here corresponding to the conductive materials in two parts here and that of the dielectric materials, we can be having alpha suffix c and alpha suffix d here. So let us proceed with the discussion. So here we consider that the attenuation constant that I have represented by alpha, and this is for the dominant mode of wave propagation or microwave propagation onto the microstrip line here. So this alpha is dependent on various factors. The first factor is that the geometry. So this geometry will be accounted by the various factors of dimensions we have represented W, T, H in this schematic diagram here. Whereas we have the another factor onto which the alpha is dependent. These are the electrical properties. And at the third place we have the frequency as a parameter here. So for the electrical properties, most possibly the epsilon, the mu, the conductivity sigma are the three parameters that give how the particular material is with respect to the electricity passage there. Next to that, as just now I have discussed the separation of alpha in terms of alpha C and alpha D here. The alpha C, we can give it the name that it is accounting the dielectric loss into the substrate here. So for the substrate we have a semiconductor material, so I just mentioned here dielectric loss in the substrate. Whereas for alpha suffix C, because of the conductor material here, I can say this is the ohmic skin loss in the strip conductor and the ground plane here. So in the conductor only I mentioned here. So what about the ohmic skin loss? See, this is because of the imperfectness of the conductive material as well as the dielectric material. When we talk about the conductor material, so the conductor material is characterized by the conductivity value. So ideal conductor, a perfect conductor should have the conductivity is equal to infinity. But practically no material is there to hold the value infinity, it has some finite value. So all these particular materials having the finite value have at the surface some kind of resistivity material represented in that particular, that it is represented by R suffix S here. So because of this particular RS, we get the losses to occur. So if the material is perfect conductor, alpha C should be ideally equal to 0, but practically there it is certain non-zero value. So it is because of the RS content there. Now in the similar fashion, the dielectric should be a perfectly insulator. So it should not allow the passage of conductivity. So conductivity ideally should be equal to 0, but practically there are certain amount of charge carriers at a very minority level that can produce or support to the conductivity value. So sigma is not exactly equal to 0 in the case of practical dielectrics. So those are accounting for the dielectric loss. Otherwise alpha suffix d should be equal to 0, but these are not the cases we have obtained while working into the practical domain. So for the determination of alpha suffix c and alpha suffix d, we take the help of determination of power. So here we shall be talking about, first of all, the power that has been carried out by the microwave signal, and it is into the positive z direction. So it can be simply represented by P, and in terms of voltage and current we can express it in the form 1 by 2 into capital V into I asterisk in the complex representation here, which in the another representation can be also mentioned to be 1 by 2 into the bracket V positive, the peak value of the voltage, in multiplication to the exponent e to the power minus alpha z. So this is with respect to the attenuation and the propagation towards the z direction, whereas the another component in commas I can give, or in multiplication we can go for, that it is I positive e to the power minus alpha z here. It can also be expressed further into 1 by 2 mod of V positive, which is squared, and it is divided by z0 e to the power minus twice of alpha z here. So here we have utilized the Ohm's law here, and we have expressed I as the ratio of V to that of the Z0 characteristic impedance. Hence V positive into V positive, the mod square has been represented here. So finally this can all be accounted into the peak value, as we have the characteristic impedance, the ratio of maximum voltage and that of the current in general I can say. So it can be represented the peak power capital P suffix 0 in multiplication to the exponential e to the power minus twice of alpha into z here. So this is the general representation that I outline, and we shall be utilizing it further to have some more computations for alpha c and alpha d. So let us name it by equation number 1. So P0 that we have represented, so it will be the power at the measurement of distance z is equal to 0 here. So as we have a microwave signal but it has not propagated after it has been provided the input, so it is the total maximum power without any kind of losses that has been represented capital P suffix 0 there. Now the attenuation constant with respect to these power calculations can be expressed as alpha is equal to minus of, we have a ratio where the numerator is the differential capital P divided by differential z here. The denominator it is twice of P as a function of z here. So this can be splitted into the two parts, alpha suffix d added with alpha suffix c here. So alpha suffix d is the dielectric attenuation constant here, whereas we have alpha suffix c which is called as ohmic attenuation constant. So let the representation of alpha in terms of alpha d and alpha c is by equation number 2 here. So in the previous equation at the numerator of the right hand side we have represented a gradient. So the gradient it was minus of differential of P of z divided by dz here. So basically gradient is nothing but the rate of change of a certain scalar value with respect to the space variation here. So as we have the differentiation with respect to the z, it is the space parameter here. So as the distance changes from one end of the microstrip line, as we have propagation of the signal towards the another end, we have the changes in the value of the power which is a function of z here. So that can be in terms of minus ddz of, in place of power value I put the representation in terms of half of V into I asterisk here. In the next step, I can also express it as 1 by 2 times minus of dV by dz into I asterisk added to 1 by 2 times we have minus of di asterisk by dz into capital V here. So we can have the differential of voltage with respect to the space changes and differential of current value again with respect to the space changes here. Further, by the use of Ohm's law, we can make the first term represented as 1 by 2 times in the bracket capital R into capital I into I asterisk here added with 1 by 2 times we have sigma into V into asterisk V here. So now here we have R. So as we know that V is equal to IR, that it is the Ohm's law in terms of the lumped elements and the network theory, circuit theory, you can say that when we have used here, and in terms of cross-sectional current density, J is equal to sigma times E, or the reversal of the resistivity, that is the conductivity, we have replacement into the second part, the second term into the right hand side here. So at the final we can express minus of dp of z divided by dz is equal to, we have 1 by 2 mod I square into capital R added to 1 by 2 times mod V square into sigma, the conductivity value. So this can be accounted as P suffix C and this can be accounted as P suffix D. So it is gradient of the power due to the conductive material and this is due to the dielectric material, I can say. So this can be the equation number 3 here. So the dielectric material is accounting to the substrate, whereas we have the conductivity portion at the two places, the strip conductor and the ground plane here. Next, when we continue, we can express alpha suffix d by the use of this PD. So it will be P suffix d, the second term on the RHS, which is divided by twice of P as a function of Z here. So let it can be the next equation 4, and we can have alpha suffix c is equal to Pc divided by twice of P as a function of Z, equation number 5 here. So both are the alphas, the attenuation constants, so those can be measured in terms of Nepers per centimeter in this particular case here. So let us address both types of the losses in some more details. We first of all go for the dielectric losses here. So we can define there are certain dielectric losses when the conductivity value for the dielectric material cannot be neglected, and in this particular situation the electric and that of the magnetic fields inside the dielectric material are no longer into the time phase. So in that case the dielectric losses are accounted in terms of the attenuation constant alpha suffix d here, and here the alpha suffix d is given as sigma divided by 2 in multiplication to the square root of mu divided by epsilon in terms of Nepers per centimeter. Now in the terms of loss tangent, the loss tangent that can be denoted by tan theta, it is equal to the ratio of sigma to that of omega epsilon. We can express this alpha suffix d is equal to the angular frequency omega divided by 2 in multiplication to the square root of mu epsilon into this loss tangent tan theta here. So this is also in Nepers per centimeter here. Now as we know that the microstrip line material is of non-magnetic type material, so in that particular case we have first of all the dielectric material separating the strip conductor and that of the ground plane, and above that dielectric material surrounding to the strip conductor we have the air medium. So considering both of them, whereas the air medium is a completely perfect dielectric. We can have some modification into the formulation that we have obtained from few of the researchers. So alpha suffix d is equal to 4.34 q into sigma divided by square root of epsilon Re here, the effective value of relative dielectric constant, in multiplication to the square root of mu 0 divided by epsilon 0 here. This can be further also expressed in the form 1.634 into 10 raised to power 3 q into sigma divided by square root of epsilon Re in terms of decibels per centimeter. So in this representation of equation, we have here small q introduced. So small q is called as here dielectric filling factor, and the dielectric filling factor q is computed as effective relative dielectric constant minus 1 divided by the actual relative dielectric constant epsilon r minus 1 there. So this can be substituted in this particular place here of q, so we can get the previous form of the equation. So in general representation, considering the overall situations corresponding to the transmission with the microstrip line here, we have the representation alpha suffix d is equal to 27.3 in multiplication to q times epsilon r divided by epsilon Re into the tan theta divided by lambda suffix g in terms of decibels per lambda suffix g here. So lambda suffix g is the guide wavelength, and it has the relation with that of lambda 0 by dividing it square root of epsilon suffix Re here. So now, with respect to the earlier relation we have seen, let us have a plot that describes the information with respect to the filling factor we have represented into the equation corresponding to the values of W by H. So in this graph, we have the filling factor represented onto the vertical axis by q times epsilon r divided by square root of epsilon Re here, whereas onto the horizontal axis we take the ratio W divided by H here. So we start at 0, then 0.2, 0.4. So this way we have here at the middle position 1.0 and 2.0 at the end. So the corresponding 1.4, 1.6 can be there onto this complete range here. Whereas the filling factor has been marked right from 0.88, 0.90, we have here 0.92, 0.94, 0.96, 0.98, and here it is 1.00 here. So here we have the different curvatures with respect to the various values of relative dielectric constant. So here we start with the relative dielectric constant epsilon r is equal to 6, whereas it is 8 for this curvature. For this line we have 9.35, the relative dielectric constant for the material called as alumina. So most possibly, as we encounter several of the problems corresponding to the microstrip line, there it will be a mention of the material alumina, which will be having the possible value of epsilon r like this here. So this is the another solid line where we have epsilon r is equal to 10. Here it is for 12. We have 14, 16 here. So this way we can go up to epsilon r is equal to 50. So next to that, as we proceed and up to the 100, if we have the scale making this completely 100, so that time we can approach epsilon r is equal to 105. So for the dashed line here. So this it was the relationship between the filling factor and that of the W by H ratio into the cross-sectional view of microstrip line. We have another plot also. In this plot we have onto the vertical axis the dielectric attenuation factor represented by alpha suffix d into the resistivity represented by rho here. So this is in terms of decibels per centimeter in multiplication to ohm centimeter here, whereas we have the same, that it is W by H markings onto the horizontal axis. So we have here 0, 0.2 here, 0.4. So this way we have at the middle 1.0, 1.2, 1.6, we have 2.0, and we have 2.2 up to this one. Onto the vertical axis we have 320, 330 here, 340. So this way we can go up to 390 here. So these are the solid curves corresponding to the dielectric materials. We have the popular one, that it is silicon, having the relative dielectric constant value epsilon r is equal to 11.8, and the another one is for the gallium arsenide material, having the relative dielectric constant value of 13.10 here. Now after the dielectric losses, we shall discuss into the details, that it is ohmic losses. So what is the reason to have ohmic losses occurring into the transmission of signal over microstrip line? The reason is non-perfectness of, here we have non-perfectness of the conductors here. Now inside the conductors, as we have the central strip width separated from the ground plane by the dielectric material, here it is the ground plate, let's say. So as we see here, the conductivity of the ground plane is most possibly found to be uniform here, whereas the conductivity into the top strip conductor is somewhat different. At the open surface we find some content of the surface resistance Rs there. So therefore the conductivity increases as we go from top to that of the bottom here. So with respect to the conductivities and the current densities, we have the schematic diagram where the structure of microstrip line we have represented here. This is the strip conductor, which is at more positive potential, carrying the microwave information onto it, whereas the another shaded portion is the ground plane here. So it is now separated by the dielectric material here. So we take the vertical axis to represent the two types of cross-sectional current densities here. So it is J1 as a function of x, whereas we have J2 as a function of x for the ground plane here. So this is for the strip conductor here. So on the horizontal axis we take the distance parameter x here. So now for the ground plane we obtain such a nature as we plot the conduction current density across the x here. So here we have ground plane, whereas as we have x again plotted for the J1 of x, we have the two curvatures obtained. So this is the curvature that we have obtained for the bottom portion. So this is bottom of strip, whereas this curvature we have obtained for the top portion here. So the thing is very clear. For the ground plane we have somewhat uniformity, but at the top strip here we have the two different curves. So because of the surface resistivity, that the portion that has been exposed to the air there. So assuming all these aspects in general, the representation of attenuation constant for the conductive material here is denoted as alpha c, and it is approximated to the values of 8.686 times Rs divided by Z0 times W here. So this is accounted in terms of decibels per centimeter, provided for the condition W by H is greater than 1 here. So in this representation, the Rs is equal to the surface resistance or the skin resistance we can say. So it is measured by square root of pi f mu divided by sigma. So it is measured in terms of ohms per square units here. Whereas Rs is also given in terms of 1 upon del into sigma, where sigma is the conductivity and del is the skin depth. So this is again in terms of ohms per square measurement. The skin depth del is determined by taking square root of 1 divided by pi f mu sigma here. So this is measured in terms of centimeters or meters there. So after the discussion with respect to the dielectric losses and the ohmic losses, we have the third type of losses also existed, as we have the microwave signal transmission with the help of microstrip line here. So these losses are called as radiation losses. So in the microstrip line, the radiation losses are calculated at the approximate value with few of the assumptions there. So the assumptions are, the first one, that it is having the TEM type of transmission there. So but it is not actually the perfect case. Most of the times we find the quasi state of TEM transmission there. The next one assumption is that there it is uniformity in the dielectric of the neighborhood of the strip here. But the practical case is that above the strip conductor we have the air material, whereas below it we have the another solid state dielectric material. The another thing in assumption is also added that we have the negative portion of the radiation from the transverse electric, which is parallel to that of the strip there. And at last we have the fourth factor, that the thickness of the substrate, that represented either by H or B, is less than that of the free space wavelength lambda suffix 0 here. So taking into consideration all these assumptions, few of the researchers have given us the relationship that we have the ratio of radiated power represented P suffix RAD to that of the total dissipated power P suffix T. So this is given by 240 times pi square in the bracket. Here we have small h divided by lambda 0, the bracket is squared here. This is in multiplication to another ratio that we have f as a function of epsilon suffix Re divided by capital Z suffix 0. So here we have capital F as a function of epsilon suffix Re called as the radiation factor, and this radiation factor is given as F as a function of epsilon Re is equal to, we have epsilon suffix Re added with 1 divided by epsilon suffix Re minus epsilon suffix Re minus 1 divided by twice of epsilon suffix Re square root of epsilon suffix Re in multiplication to the natural logarithm taken onto the square root of epsilon Re added to 1 divided by square root of epsilon Re, the effective, minus 1 here. So epsilon Re, the effective dielectric constant, and the lambda suffix 0 in this particular case can be regarded as C by the operative frequency. So in the above relationship we come to know that the radiation factor represented that decreases with the increase into the surface or the substrate dielectric constant. So therefore the alternate representation is given by the equation that we have P suffix RAD divided by the total PT is equal to R suffix R divided by characteristic impedance Z0. So in this representation, capital R suffix R is called as the radiation resistance. So we have radiation resistance R suffix R given by 240 times pi square in multiplication to H by lambda square here. So this is having the suffix 0 in multiplication to F as a function of epsilon suffix Re here. So I hope the discussion that has summaries with respect to the dielectric losses and the ohmic losses along with the radiation losses. So by the next lecture we shall be discussing about the another topic, the effective parameter corresponding to the how much energy is stored, how much energy is dissipated per unit cycle. So it is nothing but the quality factor. So I hope you enjoy learning this subject, microwave engineering. For more such information and the details, you can subscribe to Ekeeda channel. Thank you.